The next thing I want to do is talk about two common applications of the stuff that we just talked about, calculating velocity and acceleration vectors in a rotating coordinate system. These two applications are first polar coordinates, and the second one is two simple rotational motions where one is happening on top of the other one. So a superposition of these things, a piggybacking of one on top of the other one. An example of that, if you can picture what the Enterprise at Valley Fair looks like, you have one arm, like you have a spinning disc, and that disc's orientation is controlled by an arm that rotates about another axis. Those are two simple rotations, but superimposing them makes the motion complicated. And one way to make it simple again is to use a rotating coordinate system. So I'm going to start by talking about polar coordinates. So for polar coordinates, let's first think of just sort of a reference inertial coordinate system and say that there's the motion of a particle doing whatever it does. You could give the path of this object in terms of x and y, like we're used to. But for certain motions, it's simpler to give its path in terms of a distance r from the origin and an angle theta from that positive x-axis of our kind of implied coordinate system. So you might think of the coordinates in polar as being r and theta. And in a lot of the classes where you've talked about it briefly before, that's probably how the coordinates are given. But that's not actually a vector, r and theta. In order to think of it as a position vector, you need to devise a coordinate system where the axes are 90 degrees apart. And the one that we're going to use is a coordinate system where the axis ER points from the origin out to the object, and the other axis E theta is perpendicular to ER. And then in this coordinate system, the position vector is just R times ER plus, well, all you do is go R out ER and then you're there, so 0 E theta. Or in other words, you can think of it as the vector R0. So what is the velocity vector in polar coordinates? Well, if this was the position vector in fixed in an inertial coordinate system, then all you would have to do is take the time derivative of the components. You'd have r dot 0. But notice that as this particle moves around, ER and E theta change their orientations. So this is a rotating coordinate system. It's not inertial. And so we're going to have to use those corrections that we talked about. And so in order to do that, you have to recognize that our angular velocity of our coordinate system is theta dot, and I guess as a vector you have to think about what that rotation is about. Now, in order to be a right-handed coordinate system, the kind of coordinate system that we always deal with, the first axis crossed with the second axis has to give you the third axis. We don't have a name for it. You could call it EZ, but we know that the angular velocity has to be about this third axis. The way I've drawn it here, you have a positive rotation. So we'll call this 0, 0, theta dot. the position vector is r0. Okay, so let's figure out what the velocity vector of this point would be. We know that the velocity vector is going to be r dot times er. And then in addition to that, it's going to be, or actually, I'm sorry, let me do this in the other notation. So remember, v dot is equal to this is the way I gave it to you last time. So it's equal to the observed velocity vector plus the cross product of the angular velocity with the position vector. In our case, the observed velocity is r dot 0, 0. And then our omega is 0, 0, theta dot. And we're crossing that with our position vector, which is r 0, 0. If you multiply that all out and add it up, you get a vector of r dot, and then the second component is r theta dot, and then 0 for the third, which is good because we don't, you know, in polar we're talking about a 2D thing. Okay, so this is the velocity vector given in polar coordinates, and you can look that up and you get these values. A lot of times it's just sort of presented as a formula you need to remember, but this is where, you know, one way to derive it. Often it's written as r dot er plus r theta dot e theta, but that's just a different way of writing it than this. And what about the acceleration vector? The acceleration vector that I gave when I first started talking about rotating coordinate systems is the observed acceleration in that rotated coordinate system. So that's just the double dots of the components plus the angular acceleration of the coordinate system crossed with the position vector plus that Coriolis term, 2 times the angular velocity crossed with the observed velocity plus omega cross quantity omega cross p. Okay, so let's fill in our values. The second derivative of the position vector components is just r double dot 0, 0. Then you have the first time derivative of omega. Remember, omega was 0, 0 theta dot, so this is just going to be 0, 0 theta double dot crossed with our p vector, which was r 0, 0. And then we'll add 2 times our angular velocity crossed with our observed velocity, and our observed velocity was r dot 0, 0. And then finally that centripetal acceleration term, 0, 0 theta dot crossed with 0, 0 theta dot cross r 0, 0. multiply that all out and you get this sort of messy thing, r double dot minus r theta dot squared for an x component, 2 r dot theta dot plus r theta double dot as a y component. And again, that's something you can look up online. It's a formula that's often just presented. That's how you calculate it. But you can make sense out of where these come from using this idea of rotating coordinate systems. One thing you should notice about polar coordinates, maybe you remember this from other classes where you've talked about it, there are formulas for going back and forth between the inertial coordinate system that I drew on the last page with that horizontal x and the vertical y, and that polar coordinate system. And so you definitely don't have to do anything in polar coordinates, but sometimes it's useful because sometimes doing certain kinds of motion in Cartesian coordinates gets really complicated, and sometimes it's much simpler in polar. But you always could just convert from one to the other, and the conversions are if you have polar coordinates and you want to go to Cartesian coordinate, or you have polar coordinates and you want to go to xy coordinates, x is equal to r cosine theta, y is equal to r sine theta. And then if you want to go the other way, r is equal to the square root of x squared plus y squared. That's just Pythagorean theorem. And then theta is equal to the inverse tangent of y over x. Okay. So the next kind of motion that rotating coordinate systems are very useful for is when you have superimposed rotational motions. So sometimes a particle's complicated motion can be broken up into first a rotational motion of one body and a rotational motion of another that depends on that first rotation. When this happens, you want to choose a coordinate system that rotates with the first body this, like the benefit of this is that then let's say this allows you to express the particle's motion as first a rigid body motion representing body 2, and we've done that. That was the stuff that we did, you know, we did that stuff a while ago. And a correction for the coordinate system rotation. And that is the stuff that we're working on right now. Okay, so there are a lot of cases where it would be a nightmare to try to just all at once express this complicated motion of the particle, but breaking it into these 2 steps, it gets a lot easier. So let me give you an example of this kind of problem. So say that you have one disk, like a carousel, that's rotating in a horizontal plane. Let's say that it has a radius of 10 meters. And at the edge of this carousel, you have another disk that's rotating. And let's say that this disk, just so we can put numbers on this, let's say that it's 6 meters from the axis of rotation to here. Let's say the radius of the disk is 2 meters. And let's say we want to calculate the acceleration of this point P, given that this is rotating 5 radians per second. This is rotating at 3 radians per second. Okay, so think for a second about what it would take geometrically to try to figure out what this point P is doing as it moves. Like say you just wanted to straight out try to come up with a position function for this point P. It would be a combination of sines and cosines times cosines and stuff. It'd be a mess. The thing that's difficult here is we don't just have a rotation about an axis pointing straight up the page plus a rotation pointing to the right. Instead, what we have is a rotation whose axis is straight up to the top of the page, and then a rotation whose axis is changing as this thing spins around. Okay, like notice as the carousel spins around, this axis of the vertical circle keeps changing its orientation. In other words, this rotation depends on the horizontal rotation. And notice that in this case, and in always in these cases, you can't switch it to the other way. The horizontal rotation does not depend in any way on the vertical rotation. So you always have to be clear to yourself which motion's axis depends on the rotation of the other one. Okay? If you get them backwards, you get the wrong answer. But once you know which is dependent on which, you put the coordinate system fixed to that sort of more fundamental rotation, the independent rotation, and then you represent the dependent rotation in that rotating coordinate system and then go back and do the correction. Okay, so let's go through this one. So the first step, think about, so what I'm going to do is the independent rotation is the carousel in this case. I'm going to put my x-axis this way, y-axis this way, z-axis this way. And that's going to rotate with the carousel. In other words, the position of the center of this circle is always going to be, it's always going to be 10 meters in the positive x direction and then 6 meters in the positive y direction. So the first step is to calculate the observed, so in the coordinate system, the observed velocity of p and acceleration of p. So we can think of this problem, and remember this problem is one that we've already done problems like this. So our coordinate system, if we're looking, now this is that smaller circle, that vertically oriented circle. If we're looking at it from the outside, so in this picture, say that we're positioned over on the right side looking towards the left side. What we see is the positive x-axis pointing out, the positive y-axis up, and the positive z-axis to the left. The point P that we care about is here. Then our omega vector for this rotation is going to be, in the view that we're talking about, it's going to be clockwise. So the omega vector is -5, 0, 0. The r vector is going from the center of the rotation to P. So it's going to be 0, 2, 0. We're talking about constant angular velocities, so our alpha is zeros, just to simplify the calculations, but it wouldn't really make it conceptually any harder if there was alpha. So the observed velocity, Vp, is -5, 0, 0 crossed with 0, 2, 0, and we get 0, 0, -10. But this isn't the true velocity. This is just the velocity that someone would observe who's fixed in that coordinate system, someone who's standing, you know, sitting on this stump, rotating around with the carousel. And so when we eventually do our correction for the fact that the carousel, that our coordinate system is rotating, this is going to be our px dot, pxy, px dot, py dot, pz dot. Okay, and our acceleration This is the acceleration observed by someone who's rotating with this coordinate system. That's going to be alpha crossed with r, so that goes away, plus negative 5, 0, 0, crossed with the quantity negative 5, 0, 0, cross 0, 2, 0. And here you'll get a value of 0, negative 50, 0. Only centripetal acceleration. And this, since this is the observed acceleration in our rotating coordinate system, this plays the part of the px double dot, py double dot, pz double dot. Now that we're done with this, and I'm going to write down our position vector too, but now that we're done calculating the observed velocity and observed acceleration, now we can plug these into our formula for the true acceleration with the correction terms to get the actual acceleration. Our position vector is going to be 10x, 6y, 0z. So P is 10, 6, sorry, not 6, it's going to be 10 this way, 6, and then another 2 to get up to our point P. So this should be an 8. Okay. And now we're going to apply the correction. Our acceleration vector is the observed acceleration, which we calculated in the first step, plus our term related to the angular acceleration of our coordinate system. Again, we don't have any angular acceleration, so we're just adding zeros. Plus the Coriolis term, 2 times 0, 3, 0. That's the angular velocity of the carousel, crossed with our observed velocity vector, which was 0, 0, negative 10. Plus our centripetal term, 0, 3, 0, crossed with the quantity 0, 3, 0, cross 10, 8, 0. And out of all this, you get the value negative 150 meters per second squared, positive 50 meters per second squared, 0. And now this is a value that you could use in Newton's laws. Whereas this observed acceleration that we got here, you can't use this in Newton's second law because this represents a non-inertial coordinate system. But this one, now if up at that point P, say we had a person with a known mass and we wanted to figure out the forces on the person, this is one that we could plug into Newton's second law and calculate forces with.